Section 5.8, solving polynomial equations by factoring. And here we have an application that states a window washer accidentally drops a bucket from the top of a 144-foot building. The height of the bucket in feet after t seconds is given by the following formula. When will the bucket hit the ground? So what we have here is an acceleration due to gravity. Here's the building, here's the scaffolding, and we have the bucket that is dropping, and the question is, when will it hit the ground? That means, when will the height be 0 is essentially what they're asking us for this bucket. Our time would equal 0, and they're asking us how long before it hits the ground. So what we're looking at is, when will the height, and h of the bucket in feet after t seconds is given by this value. We're going to set that equal to 0. We want to know when the height is equal to 0 or on the ground, and it's equal to the following equation. As I said, this is a variation of acceleration due to gravity, with gravity in the English measurement being 32.2 feet per second squared. We're not seeing 32, but acceleration due to gravity is 1/2 g for gravity times our time squared plus our initial height. And this bucket is sitting at 144 feet before it's dropped by the window washer. So we're looking to solve this now. We have a quadratic equation. We're going to solve by factoring and apply the zero product property. Between the two terms, we should always look for a greatest common factor, which ends up being a 16. But so that we have our leading term having a positive coefficient, instead of just factoring out 16, let's factor out a negative 16. Dividing the first term by negative 16 leaves a t squared. Dividing the positive 144 by a negative 16 leaves a negative 9. Looking at what we're left with, we have a two-term polynomial. The first approach to factoring this is to consider whether it's a difference of squares, which it is. Square root of the first term is t, square root of the second term is 3, and we have a difference. It will factor into the conjugate pair of t minus 3 times t plus 3, and then using the zero product property, for these three things multiplied together to equal 0, one or the other, or perhaps both are equal to 0, 16 will never cause this equation to equal 0, but a specific value of t, perhaps with the minus 3, will equal 0. What is that value? We'll add 3 to both sides. If t is equal to a 3, this would turn into a 0 and make this true. Or if t plus 3 equals 0, would also cause this equation to equal 0. Solving for t, we end up with t is equal to negative 3. Now we're looking for time, and a negative 3 doesn't make a lot of sense for time. However, for this particular problem, that is the case. But if this had been actually a launch from ground, and let me back this up, we set our time equal to 0. The clock started when the bucket started falling, but if we reflected that curve here, and instead had some application that was perhaps a launch from the ground, we can see that this would be when it was at the ground at negative 3 before it took off, and it's just where our time clock is starting, why we're having a negative time here. And when does it hit the ground? When 3 seconds has passed, the bucket will land on the ground. We could have, if this in a different application was a launch of an item, we could have set our time equal to 0. This would have been our halfway point, and had a time here that was double the point at the top or the vertex of this curve that, as we look further at quadratic equations, we'll see is a parabola with this maximum value for this particular example being at the vertex. But a little more than we need to know right now, but in the event you have a variation of this type of problem, perhaps it'll be helpful to you. So to answer a question, when will it hit the ground 3 seconds after the bucket is dropped, we can expect this bucket to hit the ground, and hopefully folks have cleared out of the way.